Introduction to Distributed Control Systems. In this presentation, we shall be diving into one of the most critical technologies in modern industrial automation, the distributed control system. It also has the acronym DCS. Whether you work in power generation, chemicals, pharma, or manufacturing, you have likely encountered or will encounter a DCS. This system isn't just about turning valves on and off. It's the intelligent backbone that keeps complex, large-scale processes running safely, efficiently, and continuously, usually 24/7 for years on end without any major interruption. During this presentation, we'll unpack what a DCS really is, how it differs from older control methods, its key components, and why industries rely on it so heavily. By the end of this presentation, you'll understand not just how it works, but why it matters. What is a DCS? So what exactly is a DCS? At its core, it's a computerized control system, but not like your laptop or phone. It's purpose-built for industrial environments. It's rugged, deterministic, and highly reliable. The word distributed is very important. Unlike a single controller managing everything, a DCS spreads intelligence across the plant. Each local controller handles a specific area, for example, a distillation column or a boiler, while staying connected to a central supervisory layer. This design gives us fault tolerance, scalability, and real-time responsiveness. Think of it like a city's emergency response. Instead of having one fire station handling all of the calls, you have multiple stations, each covering a district, but all coordinated by a central dispatch. That is the DCS philosophy. Centralized versus distributed control. Let's contrast these two philosophies, centralized and distributed control. In the 1960s and 70s, plants used centralized systems, often mainframes or early PLCs. PLCs are programmable logic controllers, where every sensor and actuator ran wires back to one control room. Imagine miles and miles of cabling. Not only was this an expensive venture, but if one controller failed, the entire plant shut down. DCS has flipped this model. By placing controllers near the equipment, we reduce the wiring, improve the response time, and isolate failures. If controller A fails, controller B keeps running. This shift wasn't just technical, it enabled the growth of mega plants like refineries and nuclear reactors and stations, where reliability isn't optional, it's existential. Core components of a DCS. A DCS isn't a single box, it's an ecosystem. 4 core components inside it work together. First, the controllers, the brains that run the control logic. Second, I/O modules, the sensory and motor interface with the physical world. Third, operator stations, also called HMIs. HMI is the acronym for Human-Machine Interface, where humans interact with the system. And fourth, the communication network, the nervous system tying it all together. These aren't loosely connected devices. They're engineered as a unified platform, often from a single vendor like Emerson, Honeywell, or Yokogawa, to ensure seamless integration and diagnostics and support. Controllers, the brains of the system. Controllers are the unsung heroes of the DCS. They're not general-purpose computers. They run real-time operating systems optimized for deterministic response. When a temperature sensor spikes, the controller must react within milliseconds, not seconds. That's why they are hardened against heat, vibration, and electrical noise. Most modern DCS controllers also support redundancy. 2 identical units will be run in parallel, one active, one standby. If the primary fails, the backup takes over so fast that the process doesn't even notice. And yes, they can be updated remotely, diagnosed online, and even predict their own failures using embedded health monitoring. I/O modules, the senses and the muscles of the system. Let's take a moment to appreciate the unsung heroes of any DCS, the I/O modules. These may look like simple circuit boards in a cabinet, but they are the critical bridge between digital intelligence of the control system and the physical reality of pipes, valves, motors, and the sensors on the plant floor. Think of them as the sensory organs and muscles of the DCS. Without them, the system would be completely disconnected from the process, unable to see what's happening or take any action. On the input side, we have two main types. Analog inputs handle continuous signals, most commonly the industrial standard 4 to 20 milliamp current loop, or sometimes 0 to 10 voltage signals. These come from devices like temperature transmitters, pressure gauges, or flow meters. The I/O module converts the analog signal into a digital value that the controller can understand. For example, 12.5 milliamps means 150 degrees Celsius. It is important to understand from the physics point of view that when you have a current loop, it doesn't matter how long your wire is or even if you change it or the condition of the wire changes. If it's going to be 12.5 milliamps, it's going to be 12.5 milliamps over the whole loop. And the way this is done is that the transmitter controls the amount of current that they put into the wire. So the voltage could fluctuate, but the current will be set to whatever the transmitter is trying to control. And they will be able to set the current, and they can be assured that the receiver is going to get the exact same current because the current does not change in a current loop. The voltage may change, but the current does not. So this is an important physics point of view which is used in this DCS kind of systems or industrial automation to make sure that the sender and the receiver are getting the same exact piece of information over the whole distance, and that is what is called a current loop. Digital inputs are simpler. They read binary states on or off from devices like limit switches, motor starters, or emergency stop buttons. For example, is the pump running? Is the door open? The digital input tells the DCS instantly. On the output side, analog outputs send precise control signals back to the field, like telling a control valve to open 63% or instructing a variable speed drive to run a fan at 1850 RPM. Again, this is usually via 4 to 20 milliamp or 0 to 10 volt technique. Again, it is important to note that if you are going to try to say 63% or 1850 RPM and that has correlated to a certain current, by using a current loop, you can be assured that your message will be sent across properly no matter what the condition of the wire is. Digital outputs send discrete commands. For example, turn a relay on, activate a solenoid valve, or light up an alarm beacon. These are the yes-no actions that execute logic in the real world. Now here's a key design point. These I/O modules aren't crammed into the main control room. Instead, they are installed in remote I/O racks located close to the actual equipment, often in weatherproof enclosures right on the production floor or along pipe racks. Why does this matter? Two big reasons. Signal integrity. Analog signals degrade over long cable runs. By placing I/O near the source, we can minimize the noise, interference, and the voltage drop, ensuring accurate measures. Again, notice you can have, if you're using a voltage, you would have to be close to the signal. If you're using a current loop, you might need more energy, but the signal will be the same for the whole current loop. Cost savings. Running hundreds of individual sensor wires back to a control room is expensive and complex. With distributed I/O, only a single high-speed communication cable like a fiber or Ethernet needs to run back to the control room, and this dramatically cuts the installation time and the material costs for the whole system. So while I/O modules might seem like passive components, they are actually foundational to the entire DCS architecture. They enable the system to perceive and act, making real-time closed-loop control possible. As the saying goes, without I/O, your DCS is blind, deaf, and paralyzed. and no amount of computing power can compensate for that. Operator stations, human-machine interface with the acronym HMI. Operators don't stare at raw data. They interact through HMIs, which are graphical interfaces that turn thousands of data points into intuitive visuals. A well-designed HMI shows a live P&ID, which is piping and instrumentation diagram, with color-coded pipes, animated valves, and real-time trends. Alarms pop up with clear priorities, no more alarm floods. Importantly, HMIs also enforce security. An operator might see data but not be able to change set points. An engineer might have full access. Role-based permissions prevent accidental or malicious changes. And with web-enabled HMIs, supervisors can monitor operations from the home or the office or while traveling without compromising security. Communication network, which is the nervous system of the system. The network is the lifeline of the DCS. If it fails, coordination collapses. Industrial Ethernet is now the standard, but it's not like the office Wi-Fi. It uses deterministic protocols that guarantee message delivery within strict time windows. This is critical for safety-critical loops. Redundancy is built in, like dual switches, ring topologies, and rapid recovery protocols like MRP. These ensure that even if a fiber cable is cut, communication reroutes in under 50 milliseconds. And cybersecurity is non-negotiable. Firewalls, VLAN segmentation, encrypted tunnels, all of these protect both from external threats and internal misconfigurations. Control strategies, beyond basic loops. DCS goes far beyond simple on-off logic. At the base level, it runs PID loops, which are proportional integral derivative control, to maintain variables like temperature or flow. But modern DCS also supports advanced process control, APC, which uses mathematical models to optimize entire units. For example, in a refinery, APC might adjust 50 valves simultaneously to maximize gasoline yield while staying within the safety limits. It also handles batch processes with strict sequences, which is essential in pharma, where regulatory compliance demands auditable, repeatable steps. And let's not forget safety interlocks. If pressure exceeds the threshold, the DCS can trigger an emergency shutdown faster than a human ever could. Scalability. Grow without starting over. One of the biggest advantages of DCS is scalability. Imagine you start with one production line, later you add a second. With the DCS, you simply install new controllers and I/O racks, connect them to the same network, and integrate them into the existing HMI. No need to rip or replace anything. Enterprise-wide DCS platforms even allow you to manage multiple plants from a central location. This standardizes operations and allows sharing of best practices and reducing engineering overhead. This modularity is why DCS remains the go-to solution for greenfield projects and brownfield expansions alike. Redundancy and reliability, zero downtime goals. In industries like power or chemicals, downtime can cost millions of dollars per hour, or worse, risk lives. That's why DCS is engineered for high availability. Redundancy isn't just a feature, it's layered into every critical component. For example, controllers, power supplies, network switches, and even servers. For example, redundant power supplies mean that if one fails, the other picks up instantly. No reboot, no glitch. Vendors publish MTBF, which is mean time between failures, figures often exceeding 100,000 hours. That means over 11 years of continuous operation without a failure. Of course, maintenance is still needed, but the system is designed to keep running through component failures. Data logging and historians, the memory of the plant. A DCS doesn't just control, it learns. Every sensor reading, every valve position, every alarm is timestamped and stored in a historian, a specialized time series database optimized for high-speed writes and efficient queries. This data is gold. Engineers use it to troubleshoot anomalies, validate regulatory compliance, or train machine learning models for predictive maintenance. For instance, if a pump failed last Tuesday, you can replay the exact conditions leading up to it. Temperature trends, vibration patterns, operator actions. That's invaluable for preventing a recurrence of an issue. Integration and connectivity, breaking down silos. Gone are the days when the control room operated in isolation. Today's DCS is a part of a larger digital ecosystem. It talks to SCADA for wide area monitoring, to MES for production scheduling, and to ERP systems like Apache Offbiz and Dollybar for real-time inventory and costing. Standards like OPC UA and MQTT make this possible without custom coding. And secure cloud gateways now allow remote experts to assist during outages without ever stepping on site. This kind of integration bridges the gap between operational technology, OT, and IT, which is information technology, enabling true digital transformation from the shop floor to the executive dashboard. Industries that rely on DCS. DCS is not currently universal. It's ideal for process industries where operations are continuous, complex, and safety critical. In power plants, it synchronizes turbines with the grid. In water treatment, it ensures consistent chemical dosing. In pharma, it guarantees batch consistency under FDA or DRAP scrutiny. You won't typically find DCS in discrete manufacturing like car assembly. That's more PLC or SCADA type territory. But wherever you have fluids, reactions, temperatures, and pressures that might be tightly controlled over long periods, DCS is the standard. It's the silent guardian of modern infrastructure. If the process is continuous, complex, and safety critical, chances are very high that a DCS is going to be running it. Key advantages of a DCS. So why invest in a DCS when simpler systems exist? Because the ROI isn't just about automation, it's about resilience, quality, and insight. Yes, the upfront costs are higher than a PLC-based system, but over 10 to 15 years, DCS reduces total cost of ownership through fewer outages, lower energy use, less manual labor, and better product consistency. Plus, it future-proofs your organization and operations with built-in support for IoT, AI analytics, and remote access. Your DCS today can evolve into a smart factory platform for tomorrow. In short, if your process is mission critical, DCS isn't a luxury, it's a necessity. Let's talk about the value. Because implementing a distributed control system isn't just an engineering decision, it's a strategic business investment. First, improved efficiency. A DCS continuously auto-tunes control loops based on real-time conditions. This means less steam wasted in the boiler, less excess chemical used in treatment, or tighter temperature control in a reactor, all of which directly reduce energy and raw material consumption. Over time, these savings compound significantly. Second, higher product quality. In industries like pharmaceuticals or food processing, consistency is non-negotiable. A DCS maintains process variables within extremely tight tolerances, batch after batch, shift after shift. That repeatability translates into fewer rejects, higher customer satisfaction, and a stronger brand reputation in the long run. Third, enhanced safety. DCS includes built-in safety interlocks that react faster than any human operator can. If pressure exceeds the safe limit or a gas leak is detected, the system can initiate a control shutdown within milliseconds, preventing incidents before they escalate. This isn't just compliance, it's protection for people, assets, and the environment. Fourth, lower operating costs. With automatic handling, routine adjustments, and diagnostics, you need fewer operators on the floor for manual checks. Plus, thanks to high reliability and predictive maintenance capabilities, unplanned downtime drops dramatically, keeping your production lines running and the revenue flowing. Fifth, comprehensive analytics. Every data point is captured and contextualized. Plant managers can now answer questions like why did the yield drop last Tuesday or which shift has the best operating environment, using dashboards powered by historian data. This shifts decision making from the gut feeling to evidence based insight. And finally, future readiness. Unlike legacy PLC systems that operate in silos, modern DCS platforms are designed for integration with IoT sensors, cloud analytics, and even AI-driven optimization engines. You're not just buying a control system, you're laying the foundation for a smart, connected plant. Now, yes, the upfront cost for a DCS is higher than the basic PLC setup, but when you look at the total cost of ownership over 10 to 15 years, the picture changes dramatically. Reduced waste, lower maintenance, fewer outages, extended asset life, and regulatory compliance all contribute to a far better ROI. In essence, you pay more today to save much more tomorrow, while making your operations safer, smarter, and more sustainable. The future of industrial automation. To wrap up, the distribution control system is far more than a collection of hardware. It's a strategic asset that enables safe, efficient, and industrial operations at scale. As we move into the era of Industry 4.0 with digital twins, edge AI, and autonomous optimization, the DCS is evolving from a control platform into a cognitive industrial system. But its core mission remains unchanged: to keep the lights on, the reactor stable, and the water clean, reliably 24/7 for decades. Thank you. I'm happy to take any questions, whether about architecture, vendor selection, migration strategies, or real-world case studies. Please provide feedback so we can improve these courses. Would you like to enhance your business with technology? For business owners, I'm offering a 30-minute discussion on how the technologies can be used to improve their business. Even if you don't own a business, I would love to hear from you too. I am happy to connect with people who are interested in building something useful. Thank you for taking the time to see this presentation. I hope to hear from you soon. If you would like more updates related to technology and the other topics we talk about, please subscribe to the channels, for example, YouTube, Instagram, Facebook, or LinkedIn. For the most updates, LinkedIn is where we post first.